Hello again. So we're going to go over carboxylic acids, our next functional group, and the king of all functional groups because this is the highest priority group we will see, which makes it a bit easier, quite easier, when we're deciding whether on how to number, so where to begin numbering and placing locants. But first, before we get into that, let's look at the structure of a carboxylic acid. So the general form of a carboxylic acid is just this. We have our carbonyl group, which we've seen, right, on a terminal carbon, except it's not an aldehyde. Here we have an OH group present as well. So that gives you COOH as your general carboxylic acid structure attached to an alkyl end. Okay, this is an important class of a functional group, or this is an important functional group because we do see that it is found in different substances. It has unique properties because of its structure. Here we see that there is this carboxylic acid component in aspirin, acetylsalicylic acid, in ibuprofen, found in brands such as Advil and Motrin. So here we see that it's written in a bit differently, COO or CO2H. And that just really refers to the structure here, to your carboxylic acid structure here. And these are a couple of different types um, of antibiotics, and we see that there's a carboxylic acid present here. And if you look closely, there is one present here as well, drawn in a 3D representation using your standard VSEPR notation or standard VSEPR methods of depicting the 3D molecules. Okay, now the reason I spent some time going over this is because what you could get in a question on a test or quiz is a question that asks you to identify different functional groups. So you should be able to identify a few here. You might identify the alkenes, double bonds present here. This would be a ketone, a methyl group, or part of the parent here. What else do we have? All right, well, these we'll look at later. This we should know as well, right? An ether, a halogen here, right? So different, an alcohol here, right? So worthwhile exercise. Okay, now nomenclature. The only thing I want to mention here is that you would take the ending of your hydrocarbon, of your parent hydrocarbon, and you would take out the E and you would add oic acid. So if it were an alkane, it would end with an oic acid. Okay, now that sounds strange, but it'll make more sense hopefully when we get to an example, which we'll do right now. So here we have a 1, 2, 3, 4 carbon parent chain. If it didn't have this carboxylic acid group, it would be butane. So let's go through the thought process of this. We know that it is going to be a functional group. Rather, the functional group is going to be carboxylic acid. So here it is. Here's our functional group here. That is carboxylic acid. So it's going to end in oic acid. We also know that the hydrocarbon chain is an alkane. It's going to end in ane, and that it is 4 carbons long. So the root word is going to be but for butane. Now, according to the nomenclature rule, we take out the E and we get butanoic acid. Okay, so this is the answer then for example A. Okay, moving on to B, we see that we have 1, 2, 3 carbons. Normally a 3-carbon alkane, right, as this is saturated, would be propane. You take out the E and you add oic acid and we get, oops, change back to the cursor, we get propanoic acid, right, propanoic acid. Okay, now getting a little more challenging, we have 1, 2, 3, still 3 carbons, except it's not an alkane. Here we have a double bond, which means it's an alkene, and we're going to get the ending ene normally. But since we have a, where is it here? Since we have a carboxylic acid functional group here, it's going to end in oic acid. Okay, so putting this all together, we get propene, but because it's carboxylic acid, we get propenoic acid. Right now, you probably looking at this wondering, well, should we number any of these? And yes, you certainly can number, and you should. So you should get to propenoic acid. Now, we've gone over several examples where numbering wasn't necessary. Now, I say that carefully because numbering is almost always necessary, except when it's implied that it is that whatever the locant is referring to, whether it's there or not, whatever it is referring to, is on the first carbon. And we've seen several examples of that. Now here, it isn't the case where this double bond is on the first carbon. So it has to be on the second carbon. And that is specific to this molecule. Look, you can't have that double bond appear anywhere else. It couldn't appear here. The carbon can't form a double bond here, a single and another double bond there. So the only place really for this to exist would be off the second carbon. So although it can be written as simply propanoic acid. In this case, it doesn't mean that it's on the first carbon. It means it has to be on the second because it's the only possible place where that double bond could be. So to make it really general, you don't need to write a locant if the location of whatever functional group is in question is going to be obvious, right? And in this case, it is because it has to be on the second carbon. There is no other choice. I'll put that off to the side. Okay, next. Here, your numbering system has to begin on the highest priority group, which in this case, of course, is the carboxylic acid present here in red. So we start numbering 1, 2, 3, 4, 5. Now we have to make a decision. We've reached a fork in the road. We should go 6 up there or 6 at the bottom. Now we're going to stick with the 6 at the top here because we want to include as many functional groups as possible, so 6 and 7, especially since this is an alkene. So off a 7 carbon backbone, where on the 6th carbon you have an ene, right? That is going to be the parent. Also notice in green here, I believe that's green, we have a branch, an alkyl branch that is 1, 2, 3, 4 carbons long. 1, 2, 3, 4. So that's going to be butyl. So butyl exists off of the fifth carbon. Okay, so 5 butyl. Then we get a double bond that exists off the 6th carbon, off of heptene. Now it's no longer heptene because of the functional group here. It becomes heptene oic acid. So put that all together, we get 5 butyl 6 heptene oic acid. Notice numbers and letters are separated by hyphens, right? That is then the name of that molecule. Okay, continuing. Now here's another different example. Here we have 2 carbons. Now these 2 carbons also show you that you have 2 carboxylic acid. So what have you done in the past when you've seen carboxylic acids or well, I guess you haven't seen carboxylic acids like this before, but anything else that appears in multiples, we use those regular prefixes. Off of a 2-parent carbon chain, we see that it is ethane dioic acid. Now, what might stand out here is the fact that there is still that E, right? And normally it does say, the rules do say to remove that E. Now this is IUPAC grammar. Again, I'm not going to be picky with this. When you're using a prefix to describe a double carboxylic acid, of course, you can't really be more than that. You're not going to see anything else with 3 carboxylic acids present in a parent. It has to have one end, or it can only have 2 ends. Parents can only have 2 ends. So you're going to keep that E. Okay, if it's not here, again, I'm not going to be too picky, but this is just something you'll notice when you're doing when you're trying to name something and you're using a prefix. You end up keeping that E. Okay, next, I switch to that. Okay, so here, a different way of depicting a molecule. So here we have got COOH. Now, at first glance, it doesn't seem like that's a carboxylic acid, but if you were to draw the structure out, you notice that it is. So here's your carboxylic acid. That means this has to be carbon 1, this is 2, this is 3, and this is 4. Okay, looking at your molecule here, it is an alkane. Now, how can you tell? Well, from experience, by now, hopefully you'll be able to tell. Otherwise, if you doubt yourself, that's fine. Just draw the molecule. So this is going to be butane, except you have something going on in the second carbon. So we're going to be 2-chloro, right? Then you take the parent, take out the E, and you add oic acid, and this is what you get, 2-chlorobutanoic acid. Okay. Now, this is going to be a tricky one because you haven't seen an example like this, and we're going to add to the nomenclature rules that come before here. This is a cyclic carboxylic acid. Now, naming cyclic carboxylic acids don't follow your standard rule. So it's not that you take out the E and you add oic acid. That doesn't happen anymore with a cyclic carboxylic acid. Notice there's a COOH here, so that's your carboxylic acid. Then the numbering here is already done for you. This has to be carbon 1 because that's where your carboxylic acid is attached to. Therefore, this is going to be 2 because you want to give your alkyl halide or your halogens here, your halides, we want to give them the lower or as low a locant number as possible. So carbon 1 is here and carbon 2 has to be there. So alphabetically, we would write 1 bromo 2 chloro, right? And this is a cyclopentane, right? Now, we don't say as you think you would. Instinctively, you might say, well, it's going to be cyclopentanoic acid. Instead, and I've written the rule down here for you, this is the name. Okay, so start on the left and then worry about all of this business over here in just a moment. So 1 bromo because it comes alphabetically, or B comes before C. Then it's 2 chloro. Okay, all that should be review. Cyclopentane, and here's where it gets a bit messy. Now, you don't follow that rule. You stick with the parent's complete name, cyclopentane. Then you write carboxylic acid in its entire form as it is here, carboxylic acid. So whenever you have a cyclic carboxylic acid, keep the parent name, don't change it, just tack on the word carboxylic acid to the end, and that's how you name a cyclic carboxylic acid. Okay, another different sort of example. Here the rule is when you're naming carboxylic acids with an aldehyde or a ketone as branches. So what you might think this, well, this looks like here, this looks like an aldehyde, or if this were on a non-terminal carbon, you might think it's a ketone. Essentially, whenever you see a carbonyl and a carboxylic acid, the carboxylic acid takes priority. So it's going to end in oic acid, and that carbonyl, whether it's terminal or not, is going to have a different name. It's not going to be one or al as you would expect a ketone or an aldehyde. Instead, it's going to be, and I apologize for this, I didn't make up these rules, but it's going to be oxo. So this has to be carbon 1, therefore 2, 3, and 4. So off the 4th carbon, we have an oxo that exists off of butane, but we change butane to butanoic acid, put those together, and this is what you get, 4-oxobutanoic acid. Okay, that's really it for nomenclature. Now we can go over characteristics or properties of carboxylic acids. We see that carboxylic acids are very polar. Look, they have an end. If I can get my cursor back. Okay, they have this end here will give you hydrogen bonding. And your double bond O, highly electronegative and electron dense, gives you a another negative dipole, creating dipole-dipole, right? Dipole-dipole bonding, or dipole-dipole interactions, I should say. Dipole-dipole intermolecular forces exist there. So it's a very polar functional group, which makes carboxylic acids quite polar. Okay, now that being said, it can be miscible in both polar and nonpolar substances depending on its carbon chain, right? The longer the alkyl group, the more nonpolar it's going to be, right? And the more nonpolar it's going to be, the less miscible it is in water. Okay. I should actually fix this because this has something slightly, well, different actually. So COO bond is polar, that's right. Your hydroxide and your OH is also polar, right? So it is going to be soluble in water. Yes, that makes sense. Now here it says the longer the alkyl groups, okay, that would be the chain, the more immiscible with water. No, that's actually fine. The more immiscible. So I'm emphasizing this. This does not mean the more soluble it is in water. That means the more immiscible it is, means it's less soluble in water. It's hydrophobic. Okay. We can review this word. You can ask questions. Essentially just means scared, phobic of water. It doesn't dissolve in water. It is not miscible in water. Okay. The longer the carboxylic acid, therefore the more intermolecular forces, right? The greater molecular weight, if it's longer, the more solid it's going to be. So the more intermolecular forces there are, the more these molecules can hold on to each other and begin to change its state at room temperature with longer and growing alkyl ends. Okay, higher melting points than your parent hydrocarbon. Yes, that should make sense because now you have a very polar carbonyl and hydroxyl end that make up your carboxylic acid. So that means greater intermolecular forces and higher melting points, right? And this should go without saying, the more COO groups and more carboxylic acid groups you have, then the higher that melting point will be. Okay, so how you make carboxylic acids, it essentially involves an important reaction here. It's an oxidation reaction. So you need a primary alcohol for that to occur. Remembering that primary alcohols are alcohols that are attached, that are attached to one other carbon. So your OH group and its carbon is attached to one other carbon. That makes it a primary alcohol. So a terminal alcohol, if that is oxidized, given these conditions, KMNO4 is a strong oxidizing agent, a strong oxidizer, and acid, and a strong acid, a two-step reaction will take place. First, it will oxidize to an aldehyde, right? Byproduct being water. This reaction will continue, and that will give you, because it's a terminal carbon or a primary alcohol, it'll give you a carboxylic acid. Okay, important to note, and you can think about why this is the case, and we could talk about it in class or you can ask questions online. Secondary alcohols do not oxidize to form carboxylic acid. So just to remind you what that looks like, it looks like this. So think about why this can't oxidize to give you a carboxylic acid. Okay, right. So the reactions, one reaction we're going to look at is a neutralization reaction. Okay, so it does behave like an acid. It behaves like a proton donor would, and it would donate a proton like that to give you RCOOH, where again that R is any continuation of your parent chain. And what will happen in the presence then of a base, if this behaves like an acid, is a neutralization reaction, like you've seen since grade 9. An acid and a base will produce water and a salt. Okay, with a typical strong base, sodium hydroxide, that will produce a sodium salt um, of that carboxylic acid, of what was that carboxylic acid. So this is what will form, and we'll look at this reaction in a bit more detail when we do esters in our next lesson. Okay, but this is how that neutralization reaction looks like. Okay, a few more examples of where you can find carboxylic acids. You do not need to memorize this. Notice it's not written in blue like most things are that we focus on. A few more interesting places where you find important carboxylic acids. Right, and here is your carboxylic acid worksheet. Pay attention to number 10. It's a good challenge question that we'll take up in class. Hope this helped.